I'm very proud that we are kicking off 2020 with a visit from Jan Kautz, the Vice President of Learning and Perception Research at NVIDIA. His research involves deep learning, visual perception, geometric vision, and an area intriguingly named DEEPINVERSION, which refers to machine learning methods that can synthesize entirely new images and videos. I will start by giving you a little biographical background. After earning degrees from the University Erlangen-Nuremberg and the University of Waterloo, Jan embarked on his doctoral studies at the Max Planck Institute for Informatics, graduating from that prestigious research institution summa cum laude in 1999. After conducting postdoctoral work at MIT, he taught for several years at University College London, and in 2013 he joined NVIDIA as a senior researcher. He has held his current post there since 2018. For those of you who may be unfamiliar with NVIDIA, the company has been at the forefront of computer graphics since 1999, when they developed the first widely available GPU. Now, decades later, the GPU is being deployed at the intersection of virtual reality, high-performance computing, and artificial intelligence. The company likes to say that NVIDIA GPU computing has become the essential tool of the Da Vinci's and Einsteins of our time. And that seems like a fair statement, especially given the strides being made thanks to Jan's work. He will touch on some of those strides in today's presentation titled Generative Models for Image Synthesis. Specifically, he will be describing some of his exciting work with generative adversarial networks, which, as he has found, are key to solving important image-to-image translation problems. So without further ado, let's welcome him to the stage.
Great. Thank you. Thanks for the nice introduction. Good morning, everyone. Welcome. So as Anna mentioned, today I'll be talking about generative models for image synthesis. So before I start, I'd like to go back and look at the traditional graphics pipeline and tell you a little bit about how we usually create images with computer graphics. So if you want to create, like the figure on the right, what an artist needs to do is first build a mesh, usually a triangle mesh or a subdivision mesh. Then you need to assign textures and materials to that character. You might need to pose it, animate it, and then finally render it using ray tracing or rasterization. So this works really well, right? It's used a lot in games where it's been super successful. It's used in the media and entertainment industry. If you look at sort of the recent movies that were nominated for special effects, all of them use GPUs to render their special effects. It's used a lot in simulation. We use it to synthesize training data for AI, right? So it's very successful. It does come with one downside. It's fairly labor intensive to build models like this, right? So an artist needs to spend hours on building meshes and textures and so forth. And some things are really difficult to do as a result. So for instance, if you look at the character on the right, and as a human, we can imagine what the person underneath looks like, right? It's very simple. But now if you ask an artist, take away, the suit and show me the person underneath, well, there's probably nothing underneath, right? And because it hasn't been modeled, because it's so difficult to model. So as a result, we've started looking at whether AI can somehow help making tasks like this easier. In particular, we're interested in, can we help creators and artists solve some of these problems more easily? Or can we solve some of the problems like imagining what this person would look like underneath? So the task or the goal for today's talk is to show you that, or to answer the question whether we can learn to synthesize images. And by that I mean, can we learn to synthesize images from some data, maybe supervised, maybe unsupervised, and then do what we sometimes call neural image synthesis or deep imagination. So meaning we want to synthesize images that look real, but weren't created with a traditional graphics pipeline, but rather with machine learning or deep learning of some kind. So what I'll talk about today is some recent progress that we've made in this field, and I'll focus on images and videos because they're easy to show, and the use cases that I have in mind for this, at least initially, is content creation. So really help artists create content, and then generation of training data for training algorithms. So the main method that almost all the work that I'll present today is based on our generative adversarial networks, GANs. And many of you probably know GANs, so I'll just go over it very quickly. A GAN is basically a neural network where your goal is to learn to synthesize images, in our case, according to some training distribution. So you're given a set of training images, say, images of a car driving, on a sunny day, right? And now you want to build a neural network that, given some latent vector z, which you as a user give it, I want to create a random new image that's very similar to the distribution of training images that I was given. And to do this, I have a generator that generates images. And I have a discriminator, which is also a neural network that also needs to be trained, that tells me whether the image that the generator created is realistic or similar to the training distribution or not. Initially, the generator doesn't know what to do, right? It'll just synthesize some random noise. And the discriminator also doesn't know what to do, and it has to tell whether it's false or true, meaning if it's a real image or not. And the discriminator can learn, at least from some of the training images, what constitutes a real image, and real meaning similar to the training distribution. And then you train these, the generator and discriminator, in a ping-pong fashion. And then eventually, if you do it right, you can actually arrive at a point where the generator can synthesize images that are similar to the training distribution. The discriminator has a hard time distinguishing the generated images from images in the training set. And this is what we want to achieve, right? This is what a general adversarial network is, and it was proposed by Ian Goodfellow in 2014. Now, initially, the first results were okay, right? They were like, stamp size, meaning 64 by 64 pixels, and they looked okay. Since then, we've really come a long way. This is an example from last year, done by people at NVIDIA. I wasn't involved in this, but other people at NVIDIA. This is StyleGAN, Karas et al. And all the faces you see here are synthesized using a neural net, or a GAN in this case. And it's really impressive, right? You could not tell, if you were shown this image, especially one on the left, you couldn't tell whether it's a real image or not. It's really quite astonishing what you can achieve with a GAN. So we've come a long way. Now, if you use a GAN like the way I presented, they look great, but you don't have a lot of control, right? Because the only control, if I go back, the only control you have is this vector z, right? Which you give the network, and depending on this vector, you synthesize a different image. But you don't have a lot of control on what the image will look like. There are some, StyleGAN offers some control, but overall there isn't a lot of control. So how can we give the user some more control on the images that are being synthesized? One way of doing it is with a conditional GAN, where what you synthesize now is not based on sort of this latent vector z that is hard to interpret, or at least often hard to interpret, but maybe we can condition the output of the GAN on something else, for instance, on another image, right? And this other image could be sort of a nighttime image that you want to translate to a daytime image, or maybe it's a label map that you want to translate into a realistic looking image. So conditional GAN is actually very similar overall, except that the input to the GAN is not this latent vector, but some other image in our case that you want to condition the output on. Otherwise, the rest remains the same. And we do this because this allows us to sort of enable machines to have sort of some imagination abilities. And then I put this in quotes because really they don't have any real imagination abilities, but they've learned what something like this image on the left, which is taken during the day, what it might look like when it rains, right? Can I learn a function or a mapping based on some training set that will allow me to imagine what this image looks like on a rainy day? And it turns out you can actually learn this. So the output on the right looks like a rainy day image, and it was actually created using a GAN, and it does pretty well. And I'm going to show you later how we can arrive at this. Now you might wonder, why exactly do I want to condition sort of the output on an image input? Turns out there's a lot of use cases for this. Sometimes we don't think necessarily in these terms, but for instance, If I want to go from a low-res image to a high-res image, it's sort of an image-to-image translation problem, right? If I want to go from blurry to sharp, or from an image to painterly style, rendition of that image, or if I want to go from thermal to color, or noisy to clean, those are all, in some sense, image-to-image translation problems for which there are specific, algorithms usually to solve those, but nonetheless, they're image-to-image translation problems. The problems that I'm interested in today are more like the ones on the bottom left, the four on the bottom left, where I might have a label map that tells me, put a mountain here, put a lake here, and so forth, and I want to move from the left side to a real image. If I have a synthetic image, I might want to move it to a real image. If I have a daytime image, I might want to hallucinate what it might look like during the night. If I have a summer image, can I figure out what it might look like during the winter? So these are the things that we're interested in today. And of course, I can learn them. I can learn this either in a supervised fashion or in an unsupervised. And supervised here really means that I have paired training images where I have, say, if I want to go from a map of edges to a realistic looking image, I might have paired training data, and that's sort of common in deep learning. But we're also interested in unsupervised case, or at least what we can call the unpaired case, where you might have a training set of images that were, say, taken during the daytime of a car driving around somewhere. Then I have a similar training set that was taken also by the car driving around in a similar neighborhood at night, but they're not paired, right? Because it's actually impossible to get a paired training set of daytime, nighttime, because nothing will ever look exactly the same, right? The leaves will have moved, cars will have moved slightly. So it's actually impossible for this use case to even get supervised training data. So we're interested in methods can take this unpaired training data and still arrive at a solution and translate from a daytime to a nighttime. And then we can classify these methods further. Some of the methods that are presented today are unimodal, meaning when I translate from one domain to another, I only get one output. But of course, oftentimes there might be multiple possible outputs. If I want to translate from a dog pose to a cat in the same pose, well, there's different cat breeds, right? So I might want to be able to synthesize different modalities, in this case, different cat breeds. Right, so this is the way I describe them. It is supervised, unsupervised methods, and unimodal, multimodal, and we've worked sort of in this space, and I'm going to present various methods in this space. And I'll start with the more supervised methods and then go to the unsupervised methods. So this was one of the first papers in the series, Pix-to-Pix HD, which is a supervised method, but it's multimodal. And I also put up, for almost all the work, we have a code release. So if you want to use the code, feel free to get it from GitHub. So, so the first task is what I mentioned earlier. Somebody gives you a label map, like somebody might have drawn labels saying there should be a car here, there should be a road here, there should be a sidewalk here, and so forth. Can I synthesize a realistic looking image according to the labels, and can I learn this from data? And this is actually a result that you see here. And what we've done is based on Pix-to-Pix, which was originally proposed by Philip Isola in 2017, which is very much a conditional GAN, where the input to the generator is this label map, where at each pixel it tells you what object or class of things you want to have. The only difference to a normal GAN is that the discriminator also sees the label map, so that the discriminator can ensure that you actually put the right things in the right place, and it wouldn't know this unless it sees the label map, right? So otherwise, it's very much conditional GAN. Our addition is the following. So what we do is we want to make sure that the output can be multimodal. So for instance, there's cars that have different colors. I want to be able to select different colors for the cars or different types of pavement. And the way we do this, we add sort of this branch at the lower left here, where for our training set, so this is supervised, right? We have the label maps as well as realistic looking images, real images. So we add this encoder branch before the generator, where we extract features underneath each instance of objects, and we learn those features, and then we pool the features per instance. So for each car, we have sort of a pooled feature. For each pavement, we have a pooled feature, and so forth. And then during training, we learn appropriate feature encoder, and then through the instance pooling, we get this low dimensional feature map, which represents sort of the look of a particular instance. And we feed this as well as the label map to the generator and then train the whole thing. After we're done training, we extract for each instance or for each class, so cars and so forth, we extract the dominant modes. We do k-means clustering in them, which basically means we figure out this, or red cars, blue cars, white cars, and so forth. And then at synthesis time, we can, we add this feature map again to the generator, and we can select what the output should look like. So which type of car, which type of pavement, and so forth. But that's one addition. And then we change the training a little bit to improve the quality. We use, of course, a fine generator. So initially, we synthesized only low resolution images from a low resolution map. Once this is trained to the end, we add finer grained layers to train sort of the full model to achieve higher resolutions. The discriminator we use works at multiple scales because it works so that it helps with to be globally consistent across the image. And we've added this robust objective where we don't just compare pixel to pixel values, but we compare features, and we do this in the discriminator space. So it's very similar to like a VGG loss or other feature losses, except we do it in the discriminator space. We make sure that those match, which also helps with the quality of the results. So let's look at results. I hope you can see them. It's a little bright. So here in this case, I synthesize one image according to the top right, and then we cycle through different types of pavements and different colors of cars. So you can see there's cobblestone and different types of pavement. And then, the car changes color as well. And the only thing we've changed is the feature vector that encodes what the car or the pavement should look like. And then we can play some other funny tricks. We can change the labels for various parts. So I change the label from houses to trees, and then the sky we also change back to trees. So the rest remains the same. So the cars remain in the same place. Sidewalk remains in the same place. Everything remains in the same place, except we change from trees to buildings and back, and then the sky we also change it to trees. Well, this works actually fairly well. If you look carefully, you can see some artifacts, right? The car looks okay, but the license plate isn't quite right. The location of the taillights is maybe not absolutely right. So there's definitely some artifacts. If you look at the buildings, you can see, they look okay, but not perfect. And that is, if you go back to, the label map, there isn't a lot of information, right? It doesn't actually say what's where on the car. It doesn't really say where windows are in the building. The neural network has to figure out where those things should be, and it's not always easy to get the placement exactly right. So then, later that year, we extended this to the video case, where now I have a video of label maps, and I want to create a consistent video based on the stream of label maps, right? So the first thing to do is, of course, we apply our previous method, pix to pix HD, and this is what happens, right? It flickers a lot, right? It's maybe not surprising. Let me stop it somewhere. If I look at one individual image, it looks okay, right? It looks fine. If I play it again, there's no coherence between one frame to the next because nobody told it that there should be coherence between one to the next frame. So there's a lot of flickering. Also, the semantic label maps themselves flicker slightly, right? So there's a lot of reasons for this not to be, temporally coherent, and it's not. So we extended, sort of these ideas as follows to the video case. It's still very similar to pix to pix HD. What we do instead now is that we have the sequential generator that depends on the previous frames that we've already synthesized. So the network actually sees the previous frames that we've synthesized. We take the previous frames, compute optical flow, and warp it forward, so we have some idea of what the next frame should maybe look like. And then we train a network that's similar to pix HD, knowing what the previous frames have looked like, and we combine it with the forward warped image to get to a final output. Then we change the training, or we change the discriminator to be still multi-scale, but not just in image space, but also for the video, meaning we actually look at, we discriminate whether the flow is correct. So we look at optical flow, which tells us whether the flow is sort of similar to what the real flow is, which is very helpful. And we do this also at multiple scales, meaning multiple distances across frames. And then we still train the GAN with a spatially progressive method, just like before, but we extend it to also be temporally progressive. So we start with fewer frames and then add more and more frames. And then we alternate between temporally progressive and spatial progressive. So this is spatial temporal ping pong to train our network. And then when we do all this, we get this. So this is again the input. And then this is the output. So now it's, yeah, temporally more coherent. I'm sorry, it's a little dark. It's still not perfect, right? You can still see some sort of wobbly artifacts. The trees look slightly funky, and it's maybe not as colorful as before. So some things got lost on the way, but at least it's temporally coherent now. But then you can do funny things. You can also do multimodal output. So this is based on edges, as shown on the lower left. We can synthesize 3 different looking people that all do the same thing. And here we've trained on someone dancing. So now the input is a skeleton, or really color-coded skeleton, I should say. And then we can have this person on which we've trained doing different dances. And depending on what the input is on the left side, we can synthesize a person dancing on the right side. And it looks good. There's, if you look carefully again, there's still some artifacts, so it's not quite perfect yet. But it's getting there. Right, and since we're NVIDIA, we thought we should make this, or try to make this interactive, meaning we want to give user control, right? So let's say I have a steering wheel, and I want to be able to drive through a city. And instead of using a game engine, or sorry, a game engine to render the city, we're just going to use a game engine to render a label map, and then use the network trained on, I think it was Cityscape, to render images based on the labels, and then show it. So I can have so a user can drive through an environment, and then start it, influence where they're going, what they're seeing. But then the game engine only renders the thing on the left, label map, whereas the neural network renders the output on the right. So you can now drive through a realistic-looking city that was actually trained on real-world data, but it's interactive. So you can interact and steer and so forth. And this is actually, on this particular one, it looks pretty good. There's still, if you look, the windows on the building shimmer. Sometimes they move around a little bit. Again, all the network sees is the input on the left, right? So for buildings, it doesn't really know where it should place windows, so it tries to determine automatically where the windows are placed. But of course, it's difficult to actually do this consistently. Right. Then, so this was for our initial efforts in this space. And then more recently, I was actually not involved in this, but my team worked on this. I'm going to present it nonetheless. Worked on this method called GAN, which is also sometimes called SPADE. And this is taking so the pix-to-pix idea a step further, mostly in terms of quality improvements. So here the goal is for an artist to be able to paint a label map, and this is a demo. Sorry.
Looks like a simple paint app. However, instead of color palette, we have semantic palette.
You can see.
Let's pick a label.
Sorry, is this sound on? Let me turn the sound.
To replace.
There we go. So you have different labels at the bottom, and so by default, the top is sky, and the bottom is clouds, and then you can start editing, and the system will show you sort of live results on the right side of what the result looks like, and it's been trained on landscape images. And then, so if you have water and sky, if I add a little bit of rock here and there, it manages to do those. I'm going to draw a mountain in the background. And again, it's multimodal, so I can have different styles, sunset and daytime and so forth. More. Add a little bit of sand. I'm going to change it into pebbles. Again, during different times of day, or different styles, I should say. I'm going to, again, do a mountain landscape, and then I want to point out one thing, so I'm going to let it play. So I'm going to do mountain in the foreground, a different one further in the background, sky and clouds, and now it's all changed to clouds. Again, switching through different styles. I'm going to add a tree. Still playing. So now we're going to make this part into snow. And what's interesting is, even though we've only changed the bottom left to snow, the network learned, well, probably then the rest of the scene also has snow, right? So the mountain in the background also gets snow on it. I'm going to switch back again to grass and then add a little pond. And what's interesting here, so let me stop. What's interesting here is that the network seems to have learned that if there's water, it should reflect what's on top of it, right? So it learned that the tree, we should reflect it in the water. And, right, it's never told explicitly, but since all the examples had reflections, it actually managed to figure out that you should reflect, what's on top of it. And it's really quite surprising. I think I'll stop the video here and tell you a bit about the GAN architecture, which is different than what we've previously done. It's still a GAN, right? It still has a generator and a discriminator, so that hasn't changed. What's changed is how we condition the generator on the labels. So before, the labels would be somewhere sort of on the left side as an input to the generator. This is not quite the case anymore. So the input to the generator is actually the style, and I'll get to that in a minute. But then the label maps themselves, they get fed into the generator at various places through what we call these spade resonant-like blocks. And then, trained, it's similar to before, right? It's still trained like a GAN, so the discriminator and generator are trained in a ping-pong fashion so that the generator matches the training set distribution, which in this case is all landscape images. So this one of these spade resonant blocks, what it looks like is like a residual block, except with this part where the label map gets input into what we call spade. So spade is interesting. So it's this short for spatially adaptive denormalization, where we first do a parameter-free batch norm. So we normalize, just like you would in a batch norm, where we subtract, the average and then subtract by sigma. So that remains the same. What we do is we learn, the affine transformation, not sort of on a per pixel or per feature basis, right? So given the label map, we have a few convolutional layers, and then we learn the parameters for the affine denormalization on a per element basis. So we don't multiply the whole feature map by one value or by vector, right? But we do it for each pixel in our feature map. So it's spatially adaptive because for each point you get a different different transformation, which is very helpful because now depending on the input label map, it can transform the features accordingly. And we do this at multiple steps within the generator. And that works really very, very well. And it's, in some ways, you can think of it as a superset of sort of this conditional batch norm, or a superset of ADA in, which is sort of variants of this. But this is sort of the superset where you can learn on a per element basis. And this is really what makes the GAN sort of so successful and work better in terms of quality. Right. And if you want to try this, you can try this yourself online. You can go to this webpage and play with it yourself in the browser. It's not as interactive, right? You need to click to synthesize an image, but it's still quite fun. So I painted this one yesterday, and really anyone can paint a landscape. It's very easy. I'll show you a few that I've done. So this is again, labels in, so mountains, hills, grass, water, and a bit of clouds in the background. And again, you can see that the water reflects the mountain. It's sort of learned to reflect some kind of mountain. It doesn't actually reflect the exact mountain, right? It's not exactly the right shape. It's just sort of a similar shape, which is still pretty good, right? I mean, at first glance, you wouldn't notice. You have a ocean scene, sand, and ocean. Another mountain scene with trees, and then again, yeah, a little bit of a lake, which reflects the mountain. And it works. Yeah, it's pretty fun. It's very soothing. You should really try it. You can spend hours all of a sudden because it's so fun. So here we're comparing. We've taken some, I'll call them ground truth images. They're really just images. Derived a label map from it, so just run some semantic segmentation algorithm on it, and then output sort of feed that into GAN, and then output multimodal results. And you can see actually they look pretty similar to the inputs, but not identical, of course, which we don't expect this. But you can sort of different variants of your input image that are similar to your input image, but not quite the same, and at different times of day. So you can actually take an existing landscape image and imagine what they would look like under different times of day. Now, landscapes work very well because you can find a lot of training data. I've also tried this on interior, on an interior data set. This only has, I think, 20,000 images. And here, if you look very briefly, it actually looks good. If you look more carefully, you can see there's a lot of things aren't quite right, but it's also a very difficult problem. But yeah, at first glance, it looks like a bedroom or like a table with plates on it. But if you look carefully, the plates aren't quite right, and yeah, things are a little wobbly. But it's pretty good. You can also do this with faces. So if you have labels for faces, you can synthesize faces according to the labels. And if you move the labels around or draw the labels slightly differently, then the faces will correspond to it, which is great. Another thing I didn't bring in, I forgot to include the image, which is what happens when you put things in places that it's never seen. So what happens if I put sort of the ocean at the top and the sky at the bottom, right? It's never seen this example. So it does something, but it's not what you would expect, right? It doesn't actually manage with an ocean at the top and sky at the bottom. It's never seen it. It doesn't know what to do. So the results become a little funky at that point. So or put it differently, you kind of need to know what sort of natural images look like, right? If you put things in the wrong place, it also doesn't know what to do. It's never seen examples of it. So if your semantic labeling is sort of really out of the distribution of what it's seen, it doesn't succeed, which is not surprising, but it's certainly a limitation. Okay, so this was all supervised, right? Meaning I always had corresponding label maps to output. Now, what we want to look at is if I don't have that, right? So instead of paired training data, I don't have it. All I have now is two different training sets, 1 and 2, where one is, say, during the daytime and one is during the nighttime. They're similar, but they're not identical, meaning they're not paired. And can I learn how to translate from daytime to nighttime based on this? Is there any hope of doing this? Well, let's try, right? Let's just train a conditional GAN where we input daytime image and the discriminator sees the nighttime images, and we tell it, make sure that the translation of the daytime image looks like nighttime images, right? And then go ahead and learn it. What will happen? Well, the problem is that nothing constrains the output of the generator to be similar to your input conditional image, right? If you just train it sort of saying, this is my input, this is my output, do something, it'll do something. The generator will learn to output nighttime images, right? But not nighttime images that correspond to your daytime image, because we haven't actually told it that they should be similar, right? It just means that your daytime image somehow influences what the nighttime image looks like, but the location of cars and trees and so forth, they will not be the same because it doesn't know how to do that. So we need some additional constraints to make this happen. And the one we've proposed, and there's other ones you can use, is the shared latent space assumption. So we have two domains, right? Domain 1, domain 2. We use an encoder to go to some latent space, and then we use decoder, which is the generator, to actually generate and synthesize an image on the right size. Our assumption is that if you have an image in domain 1, and let's assume for a moment you had the exact corresponding image in your domain 2, which is the nighttime, they would map to the same location in your shared latent space. So the latent space would encode sort of the scene independent of daytime and nighttime, right? And this is what I want, because then I could have, decoders or generators on the other side that would take this point in my latent space and decode it either to a daytime image or to a nighttime image. This is what I want, right? The question is, how do we get there? Because if we don't do anything, if we don't have any additional constraints, if I do this, I encode my domain 1 image, my daytime image, and I decode it, it might just happen to look very different, right? These are not identical, but they're realistic in their own way, but they don't correspond to each other. So what we do, or what we proposed, is the following. We proposed that the encoders and decoders should share between the different domains. They should share weights near the latent space. And the thinking is sort of that, well, sort of the initial layers sort of remove sort of the daytime versus nighttime thing, right? And the later layers encode the scene somehow. And as such, we can share them. And the same on the decoder side, that the initial layers will create the scene, and then the final layers will create the actual look of the scene. And with that assumption, you can actually now train the conditional GAN again, but because it's shared, you actually get corresponding images. So if you can see, this is actually a corresponding image to my left and to my right, and now I can choose which way I want to decode it to. I can take my daytime image, I can create the same daytime image back, which we use for supervision during training, and I can also create or synthesize my nighttime image, and it will correspond because I've shared the weights on both the encoder and decoder sides, at least for some of the layers, not for all the layers. In addition, we also use the cycle GAN constraint, so we actually combine them, which improves the results even further. So cycle GAN is the other method to add sort of a constraint to the translation. So what does this look like? So here are some daytime to nighttime translations. Again, we've learned them on datasets that are not paired, so I've never fully supervised this. However, it still managed to figure out that the sky should be black, right? The roads are darker, but closer to you. That is because of your headlights. It's illuminated. It's a little hard to see here. It knows that the taillights, of course, are usually illuminated, so it makes them brighter. Overall, there's less color. It's also learned some things like, let me stop this here, actually play a little more, that sometimes there's lights on the side of the road. Here it doesn't quite know where to put them, so it puts them in a lot of places, right? There's a lot of street lights everywhere. Let's see, anything else I want to mention? Okay, so this is day to night. They work quite well. The next one is winter to summer. So again, it's seen winter images and it's seen summer images. Of course, they're not paired because it would be impossible to pair them. But it's learned that where there's snow in the winter, there should be either grass or shoulder. Where there's trees in the winter without leaves, there should be leaves in the summer. And there, I wanted to show you something interesting. So it's never been told what a tree is with or without leaves, right? So it tries to determine, correlations between the winter and summer images. Now, it has a hard time with electricity poles, right? There are electricity poles that don't have leaves, but it's similar enough to a tree that it puts leaves on them, which is not totally wrong, right? It's not what we'd expect, but given that it's never learned to distinguish necessarily a tree between trees and electricity poles, it decided to put leaves on them. Not perfect, but not completely questionable either. But it does manage to remove all the snow, and it does look, it removes the gray sky and makes them a cloudy sky. And so it actually works. Overall, it works very well. Here is sunny terrain translation. And again, it's learned the sky should be gray because when it rains, the sky is usually cloudy. It learns that the road should be reflective, so you can see some reflections on the road. There's also a bit, it also looks slightly foggy because of all the rain in the air. It also learned that taillights sometimes are illuminated, or they show up a bit bright, because when someone brakes and it's rainy, right, you can see sort of a bit of a glow, and it's learned that that's the case. And again, all of this is learned without any paired images. So it's not, you know, fully supervised. And it does pretty well overall. So this was, yeah, our unsupervised method. It was only unimodal, meaning you could only have one output image. And the question is,
I have one question. So
yeah.
these models bidirectional in the sense that if you learn how to convert, say, rainy day to sunny day, can you do the same model
Yes.
to invert this?
Yeah. You can, if I go back, because it's this, right? So it's learned both ways. When we train it, we always learn it both ways. So it's supervised in the sense that the only real supervision we can give it is domain 1 to latent space back to domain 1 should look identical, right? Domain 2 to latent space back to domain 2 should be identical. And then you can go anyway. So it's always bidirectional. Yes. Right. So this was, yeah, a purely unimodal model. But of course, yeah, often in my training set, you will actually see that there's multiple variations that you could imagine of the output. So if I go from a summer image to a winter image, well, it might be winter, but it might be different times of day as well, right? And I might want to be able to synthesize different times of day and it being winter, or, yeah, vice versa, right? So the question is, how can we get there? What we do is very similar to what I just showed, except we extended the latent space with sort of a style space as well, where now we decode our images into a content latent space, as well as one where we encode the style of the image, which we automatically deduce. And then when we actually translate an image, you know, say we go from big cats to small cats or house cats, we encode, yeah, the big cat into its content code. We apply some various style codes that we've learned of, you know, the house cats, and apply them when we do the translation, and it can get different types of cats. And the way we supervise this is actually quite interesting. So there's a within domain supervision where we say, well, if I have an image of a cat, right, x1, and I want to disentangle style from content, when I combine them again, I should get back the same image, right? Which is sort of obvious. So that doesn't help a lot because it would be free to disentangle these things any way it wants, right? But since we have two domains, we can actually do something that I think is quite clever. So I can take an image from domain 1. So I can take an image from domain 1, extract its style, which is style 1. Then I take an image from the second domain, and I apply the style 1 to it. So it would be, you know, second domain image, style from domain 1 applied. So it's a translation from 2 to 1, right? And then I disentangle it again into style and content. I want now the style to be again style 1, because this is what I enforced. And I want the content to be again the content of domain 2, because that's what I asked for it. And I can do the opposite, right? Sort of going from 1 to 2 and 2 to 1. And that is sufficient to actually train this model and disentangle sort of the style from the content very well. The network itself is a bit different than before, because now we have this additional style encoder that we need to feed into our generator. So this is actually more similar to GAN, except at that point, when we developed this, we didn't have the GAN spade blocks yet, so we used ADA-in, which works well enough. And then the rest is like a usual conditional GAN with the addition of style. So now I can show you some examples where ground truth is available. So we actually know what the ground truth might look like. So in this case, we go from images of edges to realistic objects. So in this case, we take shoes and handbags, and we have the ground truth here. But it's learned all these different translations that are all actually quite sensible, right? So I have different colors for the high-heeled shoes, different patterns for the sneakers, and they make sense, right? It's sort of a leather sneaker and other sneakers with two different patterns. And again, for handbag, these were the actual patterns of these and colors of these handbags. And learned, these different colors make sense, and they're all leather handbags. And here I have different patterns. One is more flowery and more blue, and then one just all black. And they make sense, right? And it's learned this without looking at sort of the paired images. I mean, in this case, we had paired images, but only for, to be able to actually look at what they looked like originally, but we didn't use any paired training data to arrive at this. And now what I thought is really interesting, we can now take images that are real and make them look like a game image and vice versa. So here we take images of Cityscape and translate them to the domain of Cynthia, which is this simulator for cars. And you can see that it managed to get to different styles. So there's one rainy, one winter, and one at sunset. We can go the other way around as well, where we take an image from the simulator and make it look like images from cityscapes. And it actually does okay. So there's different styles. It's mostly slightly different color variations because cityscape isn't that varied. But then they do look, actually at first glance, they look fairly realistic, right? They don't look like game engine images anymore, but they look like real images, which is quite nice. We've also applied this again to our summer to winter and winter to summer. And basically what it's learned that if you look at winter images, there's images with more or less snow, right? And if you look at summer images, it's learned that there's more or fewer leaves on the trees, right? So this is what it's learned there. Then we did a fun one where we translate the pose or dogs to cats, which means we translate the dog's pose to a cat pose. Since it's multimodal, we can change the breed, go through the latent space and choose different cat breeds. And then, when the dog moves, all 4 cats move identical, but there's 4 different cat breeds. And there's some more examples where we move through the latent space. I don't know if there's anything particular noteworthy. So again, we translate from one domain to the other, and in the other domain, we walk through the latent space so you can see different renditions of things that it learned. Right, I'll stop here. Then, because we can disentangle content from style, you can build the whole matrix of content versus style. So I have types of shoes, different styles, and I can apply the style to each shoe and vice versa. So you can build a whole matrix, which is kind of neat. Right. Let's see. So one more to go in terms of image-to-image translation methods that are unsupervised. So this one is a very recent addition where we wanted to do a few-shot image-to-image translation. So before, you needed a lot of data to be able to learn to go from cats to dogs or vice versa, right? But now we wanted to see if you can learn a method where you can only give it sort of 10 images, say, of a new dog breed, and maybe you can actually do an image-to-image translation with that. So this is what we're aiming for. So it's an input image of a new kind of animal, or dog breed in this case that it's never seen. Can I apply it and still do a translation? These are all dogs, but now we're doing wolves and cats. And cat only works okay. And lion, I don't know what actually is called, that animal. This one, we did it on food. It's kind of funny. And then we show it chow mein for the first time. And it manages to translate other foods into chow mein, which mostly means that it adheres to the shape of the other food, right? It doesn't look like the other food anymore, but the shape of the food is sort of maintained. And it even keeps like the plate around, like it manages to keep the background for the most part. Right, so how do we do this? Our thought is as follows. Again, if we disentangle sort of content from class, I'm still labeling it S for style, but it's really content versus class of things. So say I have a dog, it has a corresponding content, and it is also a corresponding style. So for a different dog, it might have it's a different class or style, right? Can I apply it to my original dog and get this new dog lookalike, which is the content of the first dog that I showed, but the look, the appearance of the other one. And our assumption is that if you have a good representation of sort of this the class latent space or the style latent space, then you can do this. If you don't, so if I apply sort of something that it's not seen before, which is too different, then I might get this sort of almost correct image, but not quite right. This was actually in the previous as well, where the tongue isn't quite right. It's a cat, but the tongue probably shouldn't be gray, right? It's never seen this example, so it didn't get it quite right. That's because in my latent space for the classes, it's not well represented. I haven't quite represented the manifold well enough to be able to do this. But if I have enough sort of example images to span this class latent space, I can actually do pretty well. And the way we do this is as follows. We assume we have n source classes. So in this case, it's all different dog breeds. I always take one example as the content image from one of the dog breeds, and then I use a different class of dog breeds, and I feed them as sort of the style/class images into our neural network. And it's supposed to learn a translation. It's sort of a multi-class translation problem, right? We want to learn to translate from any class to any other class of the given ones, because once we do this, the assumption is that the class latent space is sort of well enough represented that if you have a new class that's not in the original source classes, it'll still be able to do something sensible because it's seen lots of other animals that are all similar-ish in some way. So this is actually, again, very similar to all the previous methods that I've shown, except in this case, the discriminator is multi-class, so it'll actually not just say whether it's a real image, but for which class it thinks it's a real image. And just by that, you can actually train a network to do this. And now, at inference time, all I need to do is give it a couple images of my new target class and run it through my generator, and out comes the translated image. And again, the network itself actually looks very similar to the MUNIT network, except that the style now is sort of this class encoder where I take multiple images. I did use a class code. I average pool the class code, which is then fed into these ADA-in blocks in the generator. And here are a few results. And now always X is the class that I'm applying. And so it's the input, the source class. Y1, Y2 are just two examples that I'm applying to this class. So in this case, I'm translating from, the first column is from a cat to, this particular one was a French bulldog. And I do this, for different examples. So in this case, I think we're actually showing 10 images. I'm only showing 2 of them. But then, it manages to take the look of this, French bulldog, apply it to a cat, and actually get a French bulldog out, and so forth. And I can do this, for all these different classes. And it works, fairly well. Of course, it does depend on how many different classes it's seen at the beginning. The more you see during your training time, the better it will be for a new type of class. Of course, you can always find ways to break it. If you choose something that's not been represented, it'll actually fail. And here is applied to birds, different types of birds, I should say, and it does actually fairly nicely. It does sometimes change a lot of things. So here we want to apply this type of bird to this one, and it does manage to synthesize one that looks like the top here, but the background and so forth, it also changed it, right? Because we actually didn't necessarily ask it to keep the background the same. So in this case, it decided to change the background. You can play with this again yourself if you want to. Same webpage. We call it Ganimal. So you can upload your own animal's picture, and it will translate it to a bunch of other classes. So you can imagine what your pet would look like as other classes. And here I wanted to mention some of the failure cases. I think they're quite illuminating. So if I'm trying to apply, say, flowers to cats, right, it doesn't know what to do, right? Because it's never seen flowers. It's only seen animals. It doesn't know what to do. And same the other way around. You didn't span a space that is expressive enough to go from flowers to pets. And there's the question, what do you actually expect when you go from a flower to a pet? Sometimes, we might think it should work, but it doesn't. And then there's some funny failure cases where it just ignores the input completely, and it just synthesizes again the same output as the source class. Sometimes it does hybrids, and this is again all signs that the latent space that you've spanned isn't quite isn't quite covering what you need to be able to apply a new class. Right, so everything I've presented so far were all methods based on GANs, right? All basically conditional GANs of some form or another to synthesize images. Because right, so now more recently, we've been thinking, well, is it possible to do something similar with just a pre-trained neural network? Like, how much information is there actually in a pre-trained, say, ImageNet pre-trained neural network, right? How much is in there? Turns out there's actually quite a lot. So you might know about Deep Dream, right? Google, proposed this quite a few years ago, I think 2015, where the task is as follows. So you're given some neural network that's already been trained on image classification, say. Now you pick a label, such as dog, and you start with sort of a noisy image, and then you optimize this noisy image to be classified as dog by backpropagating through the network backwards, right? So you're modifying your noisy image such that it gets labeled as dog. That's your task. If you do this, right, you start with some noisy image, which is, say, Gaussian noise. You actually still get something that still looks like Gaussian noise, but gets classified as a dog. Like, it's really an adversarial example. That's really not what we're interested in. We were interested in, well, can I actually extract the information that's in a neural network and synthesize realistic-looking images? So what Google had proposed, or people at Google had proposed, is to do some form of regularization, in particular, TV, the total variation, as well as regularizing the norm, the L2 norm of the features. And then you get things out that look slightly better. It still doesn't really look like a dog, right? But then if you also use a better optimizer like Atom, you get things that look sort of dreamy, right? They look a little bit like a dog if you sort of zoom in. You can sort of see a horse, maybe, the cat, kind of, the truck, the car. They're sort of there, right? But they're not very detailed, which I always thought is surprising. I always thought that you would have sort of more information in the network to actually get better looking images out. Turns out there is some information that's not been used. So if you have a network that was trained with a batch norm layer, you actually know what sort of the mean and variance of your batches for each layer, right? It's in the batch norm. Except so far we haven't used it. But now if you do your backpropagation and you say, actually, I also want to make sure that the images I create adhere to the mean and variance of that the batch norm has learned and seen. Then I actually get images out that look much more realistic, because now the distribution of features is the same as in my training set. And if I enforce this, I actually get images that look much closer to real images than otherwise. So this is sort of low-res versions of this, but if you do sort of ImageNet on ResNet 50, you can do this, and you can actually, not perfect images, but it's surprising how much information there actually is in an ImageNet trained neural network, right? So this is ResNet 50 trained on ImageNet. And if you run this and say for pigeon, you actually get pigeons. Like, they actually look like pigeons with textures and the right pose and everything, right? This is a burger, I think some type of fish, polar bear, right? Volcano. There's also quite a bit of diversity. And you can actually get these out of pre-trained networks. So this information is all in a pre-trained network, right? We didn't hallucinate, or we didn't add any additional information. It's just a pre-trained network. So it's actually surprising how much information really there is in a pre-trained network. In addition, we do this sort of adaptive inversion of this, where, say, your goal is actually not just to generate images, but to generate training images for a particular task. So for instance, you want to do knowledge distillation from one network to another, but you don't have the original training set. So you want to do knowledge distillation from ImageNet, ResNet 50 to a smaller network, but you don't have the original ImageNet. Can I actually do knowledge distillation without it? Well, we can use our method to synthesize some training images. We do this in a loop, meaning we actually know which images we've already synthesized, and then we add as an additional constraint that the new images that are being synthesized should be difficult for the student to classify, and then you get a good diversity of images that help the student to learn what the teacher is trying to teach you, even though you don't actually have access to the original image training set at all. If you do this, we don't quite get to the same sort of accuracy, right? So this is basically knowledge distillation from resonant 50 to resonant 50 using our method to synthesize training data. So you lose, in this case, from 77% to about 73.8%. So you lose something, right? We don't quite get sort of the same distribution of the original training set, but it's very close. It's actually, I think, really surprising that this is possible, and I'm quite excited by this work. It's really quite intriguing, I think. Yeah, and with that, I would like to conclude. Thank you. Thank you. And I would like to, so these are the things I talked about. I would like to thank my collaborators. Of course, none of this was really done by me, but it was also mostly done by my colleagues and collaborators. So now, thank you.
We'll take a couple of questions from the audience.
Fascinating talk. But one question is, how much artist control do you have on these techniques? So what I'm wondering is, if you're trying to get someone to use it, right? Are the changes in the schedules, or do you see it being kind of like something that someone could actually use it for kind of like getting what they want,
Yeah.
or something that they want?
So what we've seen, GAN is actually used by artists, but not to create sort of final results, but as sort of more as a creative tool where you get sort of some initial background plate, which you paint over with what you actually want. Like you add things, you modify it. It's sort of a very easy way to get something to start with without having to draw a lot of backgrounds, which you might not care as much about. So it gives you some initial ideas, and then you paint over it. So and for that, it's actually useful now. I agree that as a tool to really create like perfect looking backgrounds, I don't think we're quite there yet. It's really sort of just to help artists create something based on it, but it's not the final output. Yeah.
So if there's a time when we create perfect videos, so that can create fake videos. So how will be a differentiate between the actual and fake videos?
Right, good question. Can we create fake videos? So in this case, I think we're simply not there yet. So anything that we've created didn't look quite real yet. So we're not quite there yet. But I think you're right? Eventually, I think we'll get to the point where it will be really difficult to distinguish, between videos that are synthesized this way and actual real videos, which is of course something, we don't want, right? We are trying to make tools that artists can use or creators, as opposed to, for other purposes. I think there's probably multiple answers, right? There's a lot of work on trying to figure out whether an image or a video was created through a neural network, say, which I think there's actually some good ideas now that help you with it. And one of them is basically, if I have an image, right, and I backpropagate it sort of the other way through my GAN, can I resynthesize it? If I can, it was probably created by a GAN, right? That's sort of an easy way to check this. Yeah.
Can we convert a human face into a cat face?
We never tried actually humans to cats. I mean, dogs and cats are sort of more similar, right? So I don't know if humans to dogs work. So you bring up a good question, right? There's certainly a limit to what you can do, right? If things are too different, like flowers to pets, it doesn't work. So there needs to be enough similarity for the network to actually latch on to something. Where the boundary is exactly, we need to do more explorations.
I have a question regarding evaluation.
Yes.
Perceptually, do you do any meaningful score about the data that are being evaluated?
Yeah, evaluation for all these GAN methods is tricky, right? So which I didn't show. For some of them, actually for many of them, we do user studies to compare with other methods, which is if your end goal is to create realistic looking images, that's really sort of the innovative gold standard. There's of course other metrics like FID and so forth, which are trying to replicate sort of a human observer. It's another way of doing it. I personally like the user studies just because that's really your gold standard. This is what if that's your task, right? Creating images for users to look at, then that's the way to evaluate them.
Let me maybe ask final question, and then we will be wrapping up and take some questions offline. So, this technology is very exciting, and in particular, I see a lot of potential in, say, collecting new data by, for example, generating more data, right? Training data. So you have an autonomous driving car, you can generate certain critical scenarios where you would like to teach the car to avoid certain critical accidental situations and stuff like that, or even for the purpose of just collecting more data, because currently the way it's done is, we have human drivers that collect a lot of data, right, which is very expensive in practice, and labeling is a whole other issue. Was this technology used in this context, or do you see a lot of potential there? Like, do you think we are there with the technology where we can start thinking of applying it to those various settings?
So I think we're on our way to be able to use these translated images as training data. However, there's still some things that aren't quite solved yet. And in some of the examples, you might have noticed this. For instance, when we did the day-to-night translation, it placed random streetlights in places, right? And that's a problem, because if you have labeled things and now all of a sudden you have new stuff appearing that's not labeled or wrongly labeled, then that's, it doesn't work, right? Because now your labels don't correspond to your image anymore. And yes, we have sort of constraints that the translated image looks similar to the original image, but they're not, I think they're not good enough to really ensure that you can reuse, for instance, labels from your daytime to nighttime image, right? So I think there's still work to be done to actually use it and be confident that your translated images are actually like good training data. So there's still work to do.
Let's thank you again, and we'll
Great, thank you so much.